Okay, so gases. So we're going to say this is one of the states of matter. This is one of the states of matter. But there's space here, man. In front.
Okay, this one is suffocating me. It's too thick.
There was impassive. Follow on, go impassive. Okay. So, this is one of the states of matter. Okay, comma. Studies have given us laws that govern. Studies have given us laws that govern certain behaviors. Studies have given us laws that govern certain behaviors of gases. Okay. We have four main laws. Did anyone look up the Gay-Lussac's law? What's the Gay-Lussac's law? Two of it. God, it is. So what did I say? We have four main laws, and they all combine to give us the ideal gas law. And they all combine to give us the ideal gas law. Bamba shy kosha, aba sharp kosha, aba ingeka napa. But challenge money all right. And this, yes. Gay-Lussac's law umfwe ni moba umfwe lobu nangani.
At a constant volume, pressure is direct proportional to temperature.
So at a constant volume, pressure is directly proportional to the temperature. And I gave you hints. I told you we talk about P, V, O, T. So if any one of these is constant, you just need to look at the others. And you know when pressure increases, the temperature also increases. Okay, but one tried it. People have to research. Okay, let's go. And they combine to give us the ideal gas law. Okay, in brackets, the ideal gas law assumes all gases are perfect. Ed Sheeran did in his studies. So Ed Sheeran, I think, has had some literature on mathematics. Ed Sheeran has talked about chemistry, atomic structure. Ed Sheeran has now also talked about gases. So Ed Sheeran talked about shape, and we have different shapes of orbitals and different shapes of graphs. He said, oh, shape of me, and I revise. And then by my wedding, he was actually talking about the ideal gas law when he was singing the song Perfect. You shall find love, you are for me. Oh, baby. Oh. Yeah, don't say I did not happen. All right. Yeah, so the what?
The ideal gas law.
The ideal gas law assumes gases are perfect. But in reality, they are not. That is why later on we're going to introduce the Van der Waals equation. At least it won't be as foreign. Even though you can't remember it, but you're not completely blank. Okay. Assumes they are perfect, but they are not. Full stop. So let's talk about the laws. So I'll talk about three. You need to revise or research on the other one. So stop spoon feeding you. All right, so the first law is Boyle's law. Okay, mnemonic. The mnemonic is going to be the boy's temperature is constantly high. The boy's temperature is constantly high. Temperature, right. So the boy's temperature is constantly high. The boy's, so boy is boils. Right. Temperature is constantly high. Okay. The boy's temperature is constantly high. So, boy, anyway, temperature is constant. So I want you to understand that these laws, we usually look at P, V, and T. It's only Avogadro's that looks at a different variable, which is number of moles. So, if temperature is constant, we are left to talk about pressure and volume. And pressure and volume, so the law is pressure, at a constant temperature, pressure is inversely proportional. At a constant temperature, pressure is inversely proportional to the number of moles. Yeah, relax. Inversely proportional to the volume. At a constant temperature, pressure is inversely proportional to the volume. Cool, okay? I'm not used to having this much space. It feels so weird. Okay, cool. Yeah, so that's the law. So the equation is going to be P is proportional to 1 over V. Giving us P is equal to K over V. Giving us P, V is equal to K. Let me complicate it a bit. If you are comparing, maybe on the side you can write, if you are comparing two setups using Boyle's law, the equation you use will be, if you are comparing two setups using Boyle's law, the equation to use will be, P1 V1 is equal to K, which is equal to P2 V2. In simple terms, P1 V1 is equal to P2 V2. Okay? All right, let's go. So I've added some juice to yesterday's naan, can I? All right, let's go. Number two. Charles' law. Do you know that there are two people that will never be forgiven in the movie industry? That one in Blood Sisters. Jenny whatever. Me, I will never forgive. Even if she's a nice person in the movie, I'll just remember what she did. She felt like. And then there's also that other one, Acrimony.
I want to sing the price.
But then even the girl misbehaved.
There are different prices. I don't even know how much the flour was. Last time it was 55. The one I bought was 50.
And by the way, girls, I should warn you, not all guys are working on batteries, eh?
I can just take
All right, let's go.
Huh?
Charles law.
500 for every 300 for every. You have baking tips.
Charles law.
Put it like 500.
Iwe. Ichicho ngomulepanga. Bale myumva. Onzo mulomo mulechita bale myumva bantu eno kati. All right, Charles law. Yes. So, what is the mnemonic? Who remembers? I know you can't remember it, but you can test it. Charles. Can you test the juice? Charles. So imagine you've opened your mouth, and then Charles pops his pimples, and then you are talking, and then you were Charles. So anyway, mnemonic. So mnemonic, we first of all need to draw Bachacha. One cha-cha. Now, Bachacha has a pimple. Jared, she left me a heat. She's exothermic, I tell you. She left me a and then Bachacha, he touches it. Puts one finger here and the other one there. And it's ready. Apaso, the skin is even a bit numb. In fact, a little bit of blood is even one cha-cha. Then he presses it and he applies the equation 2v squared sin theta cos theta divided by g to give it enough range to come into you. When he presses it and then it starts. One cha-cha. Then there is Malaba boy na besura kanwa. One lala. This is lava boy. Next time we even feels what we call a tingling sensation. Malaba boy. So this is cha-cha. You understand? Yeah. Oh my God. Remember your guts? Some consistency. Some consistency. Yeah. I'm helping you save your money because your appetite no more. So the morning, Charles is constantly popping. Charles is constantly popping his pimples. Key thing is constant P. We're talking about PVOT. Okay? So if P is constant, we are left to talk about V and T. So we're going to say at a constant pressure, the volume is directly proportional to the Kelvin temperature. The volume is directly proportional to the Kelvin temperature. The volume is directly proportional to the Kelvin. You see, I'm not as blunt because you ate these things yesterday. The volume is directly proportional to the Kelvin, but I'm adding a few things in. Kelvin, to emphasize that the temperature should be in Kelvin. So I'm going to get V is directly proportional to T. Giving us V is equal to KT. Giving us V over T is equal to K. And if you are comparing two setups where the pressure is constant, I even here have sets. I have pink. Alright, so if you're comparing two setups, you're going to have V1 over T1 is equal to K. Is equal to V2 over T2. So regardless of the conditions, the constant for one system will be the same, you understand? That's why we can choose to just forget about the constant and just equate this part to that. So V1 over T1 is equal to V2 over T2. Because they tell you at a constant temperature, the volume is 2 liters. I mean, at 35 degrees, the volume is 2 liters. If the pressure is constant, what is the new volume at 70 degrees Celsius? You get the logic? They've given you one complete set of data, and here they've given you another temperature, then they ask for the new volume. You get the logic? Yeah. Next, Avogadro's law. Avogadro's law. Avogadro's law. Okay, so Avogadro's law. Okay, Avogadro's law There's no mnemonic, it's straightforward. Volume is directly proportional to the number of moles. Volume is directly proportional to the number of moles. You get excited. Shaingira. Volume is directly proportional to the number of moles. So that is going to give us V is proportional to N. V is equal to K N. So V1 over N1 is equal to K is equal to V2 over N2. Does that make sense? How many have done gases in class? Anyway, so we end up with V1 over N1 is equal to V2 over N2. Make sense? All right. Then number 3. That is, number 4. Number 4, research on the Gay-Lussac's law. You need to research, but I gave you ideas. What do you want to? If you keep being casual, Judith, how are you? Judith Muntabit, all right. If you keep being casual with your school, you will end up a casual. You white na munini. One you white, then I make casualties, Yeah. How many two? It seems wrong. So worry about it. All right, so I can't wait for your test 1. Please use the documents. I keep saying this over and over and over and over and over again. Let's go. Hello, it will hurt you. You know, I'm not Chikopo. I'm sure I'll just get a question. What do you want to quantum document? It's going to be a beautiful moment. Then you're going to sit on your bed. Then you're going to look at the lights. Ukadoresha sweeping rota. Ukaepa window, kesude window. Kadoreshe vamonko varepita. Wadi sana. Why mini na kuto? Wachita so. Vakonkonja autatureshita. Yeah, if I don't be the director. I must dress Mukapurisha Kunani. All right, Gay-Lussac's law. So all those combine to give us the ideal gas law. So the combination is the ideal gas law. Ideal gas law. Do you guys remember what an ideal transformer is? Yes. So an ideal transformer with 100% efficiency. You assume it's perfect, eh? Yes. But in reality, we never get 100% efficiency, the eddy currents, the what. Okay, so the ideal gas law is basically just an equation. P V is equal to nRT. All the other constants that we had combine to give us a new gas constant. Maybe you can, after I write this, you can say the constants, or all the other constants, combine to give us a new gas constant, R. All the other constants combine to give us a new gas constant, R. R. And Judith is going to tell us what R is. But Juju. For me that What's your friend's name? What's your name? Itaone, tell us. You can read. You can read. Okay, so R is equal to what? Okay, Baneba. Your name? You know this minus. No, now we should always have you have the white shirt. Judy, hi. Hi, just wait. Baneba Waka Judy. Hi. Now the person next to you, can you say hi to them? The person, yes, it is you. What's your name? Eh? Mirabel. Yes, Mirabel, tell us, what is R? Yes, but what's the value? 0.08206. Not 06, 206. For now, I'm not really interested in the units. I actually want us to derive the units together. You understand? So, then just say, in the ideal gas, okay, pressure is in atmospheres, volume is in liters, pressure is in atmospheres, volume is in liters, N is in moles, pressure is in atmospheres, volume is in liters, N is in moles, and temperature is in Kelvin. And temperature is in Kelvin. Meaning, okay. Yeah. Next thing. Okay, so I want you guys to make R the subject of the formula in the ideal gas law. What's your name? Huh? Tinashe? When did it? When? Vaniga? What's your name? Aga. Tinashe. Aga. Your friend is always complaining, but yo, Wendy, stop. I saw a meme today. Ladies usually introduce each other. Oh no, this is my friend, her name is Mary. Oh, this is my friend, her name is Mwanza. Ladies, but then guys rarely introduce themselves. And then there was a comment that says, we just wait until someone who knows that person calls you. Because it's weird. My name is Beck. Oh, sorry. All right, so we have PV is equal to nRT. We make R the subject. So I can also write it as nRT is equal to PV. Okay? Next, I can divide this side by NT, divide this side by NT. I get R is equal to PV over NT. Okay? Now, you're going to say at STP in brackets, standard temperature and pressure, we have a temperature of 0 degrees Celsius. At STP, we have a temperature of 0 degrees Celsius. RTP is known as 25, right? 25 or 24. At STP, we have a temperature of 25, of 0 degrees Celsius, and if we are looking at 1 mole of a gas, and if we are looking at 1 mole of a gas, and if we are looking at 1 mole of a gas, we will find that the volume is 22.414. But that's for babies. You find that the volume is 22.414. So add the 14 in front of what you know. Okay, excuse me. Did I mention the pressure? Okay, 22.414 when the pressure is 1 atmosphere. 1 atmosphere standard. Standard temperature and pressure. Should be fasting. Okay, excuse me. Basically, what I'm trying to say, basically, STP is 0 degrees Celsius. STP is 1 atmi. Then, if you're dealing with 1 mole of a gas, N is equal to 1. You find that the volume is 22, minus 22.4, but it's actually 22.414. Some literature may even say 412. Okay. Derive an approximate value of the gas constant and predict the units. Derive an approximate value of the gas constant and derive the units. It's actually a question, man. Oh my God. Derive an approximate. Approximate doesn't start with H. Derive an approximate value of the gas constant and predict. I don't know what Chile pole. What happened? Chile pole. Yeah. Chile did that because Nangwa am kuno wala. Yeye did Chile pole baby. One nothing. Yeah.
It's predicted.
Which beer do you like? You should try Bose and then you use Black Label as the mixer. Then when you finish, you should drink Omunkoyo mixed with chibuko and yogurt and sour milk. And as you go home, buy a big roll of tissue paper to get ready. All right, so they're asking us to calculate the approximate value of the gas constant, and they're asking us to predict what the units will be. Okay, let's go. So we are going to have R is equal to, if we have 1 mole, the pressure is 1 atmosphere, yes. 1 atm. What's the volume? 22.414. That would be liters divided by how many moles of a gas are we talking about? 1 mole. So we're going to have 1 mole times temperature should be converted to Kelvin. To convert temperature to Kelvin, we always add 273.15. You get? Now, I want you to understand the question. It is saying find an approximate value. You understand? So don't give me a headache if it's not the exact. It is 0.1. Okay, so temperature here, 0 plus 273 would be 273.15. Now let's deal with the units first. On top, the units will be atmosphere. Okay, let's deal with the numbers again. Okay? What is 1 times 22.414? So basically, just divide this by that. What do we get? 0.08 2057. You understand? Mm-hmm. Now, the units. On top we have atmosphere and liters, right? We prefer to start with liters. Why? It's just the way it is, right? Liter, atmosphere. I don't even start with liters. Divided by, below it will be more times Kelvin, eh? We prefer to start with Kelvin. Per Kelvin, more. Remember me giving you something like that, eh? So if you had to round this off, you'd get what? 0.08206. You get?
Yes.
But then if you're not careful, like I was with the decimals, like you guys just know 22.4, you understand? You may arrive at a slightly different value, but understand that that is an approximation. Does it make sense? Okay. So at least you see that we can use the basic data that we know to derive the constant. Eh? So it's not something that comes from the blues. Okay. So you can write the title, Conversions. 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 Yes. Sorry? What properties? Can you speak up? To describe the gases. I'll talk about them under the kinetic molecular theory. You get? So basically, the main properties for gases is a gas will exert pressure, a gas will occupy space, and at a certain temperature something will happen. And the amount of gases is the number of moles. And all these have a special constant, R as 0.08206, basically. You get? Okay, where are we? Okay. It's okay. I just wanted you to have a feel.
Atmosphere, yeah.
Okay.
Because atmosphere,
okay, conversions, eh? So, temperature, the first one, temperature in Kelvin is equal to temperature in degrees Celsius plus 273.15. That's the first conversion. Next, 1 liter is equal to 1 GM3, which is equal to 1,000 milliliters, which is equal to 1,000 CM3. But they are most. Oh, CM3, it's cubic centimeters. Right. Now, there's something else I want you to be able to do. You also need to know how many CM3s are in 1 cubic meter. You understand? Okay, maybe you can just put a question. How many CM3s are in 1 M3? It's not M3, it's M cubed. Yeah. This looks like Marie. Yeah, we need to correct certain things. Hi. Right. So, these units are both cubed, but they are all looking at length. You understand? For me to get volume, I need to have cubed length. Eh? So basically, let me look at the primitive relation. The primitive is centimeter. How does it relate to meter? You understand? So how many centimeters make 1 meter? 100. So 100 cm is equal to 1 meter. Okay? So let me convert this. Let me form a cube out of all this. This cube, this side is 1 meter. Okay? This side is also 1 meter. And this is 1 meter. Okay? 1 meter is the same as 100 cm3. It's the same as 100 cm3. It's the same as 100 cm3. Okay? So the volume of that cube will be 1 meter cubed. Right? Now, in terms of cm3, what will it be? I basically just have to cube both sides. You get? And if I cube this, I'm going to end up with 6 zeros. 1 times 10 to the power 6 cm3 is equal to 1 m3. You drive the relationship. Okay? Because you may need cm3 if they ask you to derive the alternative value of the gas constant. We don't only have one gas constant, there's another one. But for now, I think because you're babies, I'll let you digest this one. Okay, we are cool. The other conversion is for Jamani put numbers.
Hello, driver. Put some pressure. Pressure.
Pulation.
What's it be? Why the population?
Population, why do you got the population? All right. First year is a magical year. It's so nice. It's very, very nice. It's nice. And I think I understand why first year was easy for me. Like I was thinking about it. I did the things that you guys find too primitive to do. I studied. Yeah. Now, some of you study, but the truth that you don't want to hear is you studied wrong stuff. My advice is before you can touch anything else, I'm not saying don't job anything else. Study a quantum document, because to prepare a quantum document, I get data from Zumda, I get data from Raymond Chang, I get data from past papers, I get data from experience, what. Put it all in one document. So for you to get what is in that document, you need to study Raymond Chang. When you finish, you need to go to Zumda. When you finish, maybe you may need to go to general chemistry. When you finish, then you can study your lecturer's notes. When you finish, maybe you can go to your YouTube thing. When you finish, then you can ask around for you to get what is in one document. And that's why your friend appears to job very little, but they know more than you. And you keep studying even harder, jobbing the relevant things. And then you notice that, I don't know if this happens, but you notice that the more documents you do, the less you will want to use anything else. Yeah. The only sad part about those documents is they've never really been tested. Like, we've never had people who used them and actually wrote an exam and passed. That's the only sad part about those documents. Right? We have? Oh, we even have. You see? We've had people who've used the same documents from 2017. I taught 2017, 2018. Then there was the 2019 group. We had the 2020 group. You guys are what? 2021, 2022. Yeah. 4 groups so far have used those documents successfully. And those documents have then been more simplified for you guys. A fool is someone who does. Wow, and the same thing over and over again, expecting different results. Yeah. Because some people apparently know. It's sad because the word try doesn't have an F in it. Yeah. But if you could really see, I think you see an F. And then the E, I don't know how you spell embarrass. Yeah. And then the D is probably the grade that you end up with. The R, I'm not too sure, but I really feel it is repeats. The I is insolent. When you get chance to listen, you too, listen. Okay? Anyway, let's go. I've stopped attacking people because today is my birthday. You were an idiot, say. So pressure, we have 1 atm is equal to 101,325 pascals is equal to 760 millimeters of mercury. Do you know the device that we use to measure the blood pressure of a person? Do you know the name? Stethoscope. Stethoscope, who knows? Barometer. Okay, it's a special type of barometer. It's a sphygmomanometer. So this is going to be Newton per meter squared. Those are the alternative units. And then this is also going to be referred to as torr. Torr. So when you hear lecture, Torricelli, but you should act some confused in class. Such a lecturer feels like he's got you, but he's got you by the name. I'm sure in his mind he's like, but now he's on to test. Don't we pop all the test. Ukudia sana lecture echunga na papa. These kids, but they wale fulunga now. Come fulunganya. I show kuchita so na watch so. All right, so we are done. Yeah? Okay, next. You can write the title, Kinetic Molecular Theory of Gases. And these are free marks. The way you have free marks under dimension analysis, the uses and limitations, these are free marks in chemistry. Know the laws and know the KMT. Right. Kinetic molecular theory of gases, whatever. Also referred to as the kinetic molecular theory postulates. So they may say, states the postulates of an ideal gas, or state the kinetic molecular postulates. Okay, so there are 4 postulates. There are 4 postulates. And who knows what mnemonic we use for the kinetic molecular theory? Anyone who knows? Anyone who knows?
Amba siukumia maboko.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. What's the mnemonic? Where did you find the mnemonic? When did you use the document? It was even posted. Oh. But it's from the document, right? Anyway, let's go. Alright, let's go. Shut up, buddy. So, mnemonic. No pressure, my guy. She is Kelvin's girlfriend. How do you spell girl? Girl. How do you spell girl? Girlfriend, comma, I am not attracted to her. Yeah. No. Like, I didn't really care whether he could even remember it. I just wanted to what? To reward the efforts of someone genuinely wanting to pass. Yeah. So she may have repeated. Okay, let's go. No pressure, my girl. She's Kelvin's girlfriend. I am not attracted to her. Okay, so, excuse me. So the no is one of the postulates. The pressure is one of the postulates. Kelvin is one of the postulates. Not attracted is another postulate. So there are 4 postulates that you can pick from that remaining. Okay. The first one. Now, I'm expressing these in my own words, right? So if you study your books, you see something similar to this. Okay. Anyway, I think I'll start with pressure. So I'm going to say the gas molecules, the first postulate, the gas molecules hit the walls of the container. So gas is in the container. So the gas molecules hit the walls of the container and exert a pressure. So pressure is basically due to the gas molecules hitting the walls of the container. So pressure, why it's over there. Hit the walls of the container and exert a pressure. Look. This is the wall of the container there. Gas molecules are always moving, you understand? So imagine this is a gas molecule, it's like a ball. Any matter is going to have some space. It occupies some space. Eh? Matter is anything that has mass and occupies space. So if it has space, like my palm has some space, if I hit this non-gun, like if this is moving and it hits this, it will exert a force, you understand? So this, when it hits the wall of the container, it will exert a force, right? There's a force, and this force is in contact with the wall only on some area. This is the whole thing, maybe only this part is in contact. See? This whole part is going to have an area. Force per unit area. What is force per unit area? Pressure. So all these small forces per unit area ends up exerting a pressure. Does that make sense? Okay, next. The gas molecules are assumed to neither attract. The gas molecules are assumed to neither attract nor repel each other. So that's the not attracted line. The gas molecules are assumed to neither attract nor repel each other. But when I teach you biology, we are going to talk about hydrogen bonds. When I teach you water. Okay, next. We'll talk about Kelvin. You're going to say the third one, the average kinetic energy, is directly proportional to the Kelvin temperature scale. So the word Kelvin, the average kinetic energy is directly proportional to the Kelvin temperature scale. It's directly proportional to the Kelvin temperature scale. Okay, we are left with one. No. So the no is gas molecules are assumed to have no volume. That's a simplified version. But when you go to the book, they're going to say the dimensions of each gas molecule are so small compared to the dimensions of the container they are in that they are assumed to have no volume. The key thing is gas molecules are assumed to have no volume. Like the only volume you are looking at is the volume in which a gas is. But you don't look at the volume that each gas molecule occupies. You get what I mean? It's like you have a container and then you put in a bowl. The bowl is going to have some space. It's going to occupy or take up some space. So normally we assume that the space that the bowl is taking up is just 0. You get? So those are the 4 postulates of the kinetic molecular theory. Tell us 2 of the postulates of the kinetic molecular theory. Your name and 2 of the postulates. Somebody is smiling. Your name and 2 of the postulates. Yeah, tutule, chitule.
The first one is gas molecules are assumed to have no volume.
Okay, gas molecules are assumed to have no volume. The second one?
The gas molecules occupy.
Okay, stop. Tell us one of the laws. So he's mentioned the no part.
Gas molecules assumed to have no volume.
You can read, you people.
The gas molecules exert the pressure on the walls of the container.
Okay, they hit the walls of the container and exert a pressure test? Yes.
The gas molecules are neither to attract
No repel. Okay? Next, Mike.
The average kinetic energy determines the Kelvin. The average kinetic energy is directly proportional to the Kelvin.
So when we're talking about determines. Okay, so around that. And then Salome, what mnemonic do we use?
No pressure, my guy. She's Kelvin's
Yeah, hello from Landa, women, guys. No pressure, my guy. Shan. Nobody more for about attraction. Okay. So, now we're going to say, just a general point, the postulates assume the gas is perfect. Because some of those postulates do not make sense. Can I teach you how to teach you? Don't know if you'll be able to get it. What did I say? The postulates assume the gas is perfect, comma. In reality, it is not. In reality, it is not. And 2 of the postulates mentioned above do not apply to real gases. So those 4 postulates only apply to ideal or perfect gases. But 2 of the postulates do not really. Hey, there are 6 points. There are 20 points. AI reality. Share 6 points. Share 20 points. Shan. Nishi, all right. So excuse me. Do not apply to real gases. So we have ideal gases and real gases. Hey, don't forget. 2 of the postulates do not apply to real gases. 2 of the postulates do not apply to real gases. 2 of the postulates do not apply to real gases. Right. What do you think those postulates are? Which ones? Try guessing. The one for volume, and the other one?
The attraction.
Okay. So, yeah. you're going to say, in reality, next point, in reality, each molecule actually has some volume. In reality, each molecule actually has some volume. In reality, each molecule actually has some volume, and molecules always attract or repel each other. And molecules always apply or repel. Yeah, always attract or repel each other. Yeah. Okay. Yeah, so they may ask you which of the two postulates of the kinetic molecular theory do not apply to real gases. Okay, cool. So you're going to say, real gases can't use the ideal gas law. And it makes sense, right? Because the ideal gas law is based on those four assumptions. And two of those assumptions are wrong. Real gases cannot use the ideal gas law. Comma. For a real gas to use the ideal gas law, we need to make two corrections. For a real gas to use the ideal gas law, we need to make two corrections. And the resulting equation is what we call the real gas equation. And the resulting equation is what we call the real gas equation. Also known as, Susan, what's her name for the real gas equation? The Van der Waals equation.
What we call the real gas law.
What we call the real gas law, also known as the Van der Waals equation. We actually have the same Van der Waals is a person that studied the attraction between molecules that are not charged. And those attraction forces are called Van der Waals attractive forces. You understand? Yes. And it makes sense. The person who suggested that attraction forces actually exist should dispute the fact that, should dispute any postulate claiming that the molecules do not attract or repel. Okay? Okay. So we have to do two corrections, right? Okay, so after full stop you can say, we add to the pressure and subtract from the volume. And I'll explain the logic behind it. I know the pressure may not make sense, but the volume will make sense. We add to the pressure and subtract to the volume.
Subtract from.
Or subtract from the volume. Yeah. Brainiana. We add to the pressure and subtract from the volume. According to the number of moles. According to the number of moles. This is the most boring part of the lesson where you need to give the basic what. But very soon, it's gonna be sassy. The document gases is actually on the website. The document that has more concept, it's also the one that has gases. Yeah. All right. So the ideal gas law is PV is equal to nRT. Now let me explain. Let me try and explain. Just go. We have a container, and this container is 10 liters, right? If I was to pour water in this container until it gets full, how much water can I pour in? 10 liters, right? Okay, makes sense. So if a container is 10 liters and I pour water until it's very full, that water is 10 liters, right? What if I put in my small balls in here. And this ball is 1 liter, this ball is 1 liter, this ball is 1 liter. These are the black balls, right? Or stones, eh? And I pour water in. How much water can this container take? You know, it's a 10-liter container, eh? But because I'm considering the volume of each of the contents inside, I can't say the amount of water that I've... Yes, it's a 10-liter container, you understand? But the amount of things that can go in is not 10 liters because there's already something inside. You get what I'm trying to say? The only thing that can go in is 6 liters. So, in an ideal situation, I would say, I have a 10 liters container and there are 4 particles there. You get what I mean? In an ideal situation. But in reality, I'm going to say I have a 10 liters container, yes, but only 6 is usable. You get the logic? So, the true volume here is going to be 10, like for me to find the volume that is actually usable, is going to be the volume that I have minus the volume of each particle, 1 liter times the number of particles I have, right? You get what I mean? That is what I was saying, according to the number of moles. The more moles you have, the more particles you have. I wish I could go deeper, but now let me furunganya. You are just babies. Okay, let's go. So, what do you think I should do to the volume given? I should actually subtract from it. Now, volume and pressure, what relationship do they have? An inverse relationship. So if one decreases, one should increase. So if I subtract from the volume, the logical thing to do is add to the pressure so that that proportionality is maintained. Does it make sense? That's why we said we add to the pressure and subtract from the volume. So the pressure may not make sense if I was to try and explain, so I'll just explain the volume. So I will add to the pressure and I will subtract from the volume. Like, this stuff is actually deeper than I'm presenting it to you. And I could go deep, but for what? Okay, so that will be P plus, we are adding something, just that what we add is A over N over V squared. Remember, N over V is what? Take concentration. Yeah. So, which you get. Then the A is just a special constant and it's always given, right? Then what are we doing to V? V minus, subtract. Normally I should just subtract B. Now do you remember what I did when I was subtracting from 10? I multiplied by how many particles I have. You understand? Now the number of particles corresponds with the number of moles that I have. The more moles I have, the more volume I'm supposed to subtract. The less moles of gases I have, the less volume I'm supposed to subtract. So what you have to subtract is sort of related to the number of moles. So I'm going to subtract NB, where N is the number of moles. Do these corrections make sense? And this part, nothing changes. The temperature is still the same. It's not affected. Remember, the postulate for kinetic energy and Kelvin temperature was correct. You understand? So it's equal to nRT. We still use the same R as before. So this is what we call the real gas equation, and A and B are always given. So they'll give you A and B, and they may ask you to find anything else. In the document, I think I did some examples. Yeah. So I actually want to even do an example here. So that's very patient. So, this one is SAS. This is SAN. You find it. Okay. So, chapter. Next, How many are you? Yeah, you look. Now move to 5,000. All right, Malaya. Tamakosa no kosa. Saraka pondoi. It's just an two non to asharam gato hakana. Okay, so let's see. Are you ready for this?
Are you ready, brother?
Okay, you can write a title. You have to be what? When last did you learn us week? This week. You have to catch up. You understand? Me, I care about you, not just you, but even you. Just the two of you. Okay, even you. Okay. All right. Yeah, you guys, we have to catch up. I know. Do you know I care more about your passing than you do?
Yes.
Because I'm doing this for selfish reasons. Like, okay, the truth is I don't even care about you. Like, let me just be honest. I don't really care about you. But if at the end of the day I can get to make a very nice video for results, then it will benefit me. Like, that's just the honest truth. Now, how can I make a nice video for results? Like, that has nice results. You guys have to get nice results. So, even though I'm doing it for selfish reasons, I'm forced to care about you. Because you're the only ones who can give me those nice results. So, guys, I care about you. Here, goofy. All right, let's go. What did I say?
Write the title.
Get out. Okay, let's see. What did I want to teach you? Finger from Fuloxambilisha. No. I need to teach you density of a gas. I need to teach you what. So I'm trying to see. Oh, yeah, sir. Yeah. All right, so you can write a title. Yeah. No, relax. Anyway, don't put me under pressure. Why you messing with my... No, serious. Yeah, he said, yeah. Nala, rubber shake. Rubber. Problem, maybe not jugo. All right, this is serious. I never thought Papula was this powerful. Okay, let's see. Let's get an overview. So So we've done the KMNT, we've done that. Oh yes, rather shaken. So the title: alternative value for the universal gas constant. I didn't want to teach you this, but I think I underrate you. You guys need to shekulu. You can get so many things. Mike, move in there, alternative value for the gas constant. So I told you the only value for the gas constant is 0.08206. I'm sorry, like your ex, I like it. So now I'm being truthful. I like it. Or her. All right, alternative value. All right. Okay, use the ideal gas law and make R the subject of the formula. Yeah? Alternative value for the gas constant. Relax. The title is alternative value for the gas constant. The first point is use the ideal gas law and make R the subject of the formula. Okay? All right. Next, use STP conditions. STP conditions, they give you temperature and pressure. So there's a lot that I need to teach you. Gases is heavy. Very, very heavy. Use STP conditions, right? In brackets, STP, that is 0 degrees Celsius and 1 atm. Use standard temperature and pressure conditions. Okay, next. Look at the volume occupied by 1 mole of a gas. Look at the volume occupied by 1 mole of a gas. So STP, what's the volume? Yeah. But, so look at the volume occupied by 1 mole of a gas, but convert that volume to cubic meters. That's why I gave you that relation for cubic meters. It wasn't for play. But convert that volume to M3 cubic meters. Okay. Okay. So I want someone to define work for me. What is work? Batipi. Batipi. A Dominican. Fumen data. Huh? Force times distance. What is the unit for force? Newtons. What's the SI unit for distance? Okay, so what are the units for work? Newton meter. Newton meter is as good as joule. So wherever you see Newton meter, you can replace that with joules. I'm just saying it because that's what we're going to have to do. So PV is equal to nRT. So do you see that we keep going to the ideal gas law? Even when you derived the formula for density yesterday, it was ideal gas law. The Van der Waals equation came from the ideal gas law. Blah, 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 ideal. What? Just make R the subject. We get R is equal to PV over NT. Okay? Now, the data flow. Imagine umusevanya mwawekera data takwete tawapasa nokupasa. At this nangu wawa, but you're able to say, man, but natural gas constant. You understand? So data temperature is 0 degrees Celsius. But do we use temperature in degrees Celsius? Okay, we use temperature in Kelvin, so which is 273.15 Kelvin. You need to know this in your head. Next, pressure is in atmospheres, 1 atm. Oh, I didn't mention. You also need to convert the pressure from atmospheres to Newton per meter squared. Maybe you can put that point somewhere. Convert the pressure from atmospheres to pascals. From atmospheres to pascals. Which? From atmospheres to pascals. Yeah. And you know 1 pascal is as good as 1 Newton per meter squared. And you remember the relationship there? 1 atmosphere in terms of Newton per meter squared is 101,325 pascals, or Newton per meter squared. Do you understand why we need to convert the volume to liters? Because dimensionally we now have meter squared, meaning we need to have meter something there so the meters can cancel out. You get? Okay, let's go. What else? We are dealing with 1 mole. N is equal to 1 mole. Chapter. Oh, volume. Volume is 22.414 liters. Now we need to convert this to cubic meters. Let's do the conversion. I hope this hasn't moved. It's okay, okay? Okay, cool. Beautiful, I tell you. It's so nice. So, we need to convert this to cubic meters. So, I'm going to say 1 liter is as good as 1,000 cm3. Meaning, if I have 22.414 How many CM3s am I going to have? So X is going to be, this point is going to move, so 22, 4, 1, 4, CM3. Okay? We are okay up to there? Next, remember the relation that 1 times 10 to the power 6 CM3 is equal to 1 M3. Yeah. So, what time was I supposed to see the other people? Nice. Oh, 13 hours, eh? Okay. Yeah. What promise did I give you yesterday? That I'm just meeting you today, eh? So today, Group A was not part of the plan. I just didn't want them to attend your lesson. That's why I gave them another time, but they're not coming. Let me cancel. Just relax. Oh, I'm live. Okay, so let us continue. So, here we're going to have 22414 is equal to X. So let's find who your X is. After we've bathed. Now is it talking back?
Oh my God.
Okay, cool. So what are we going to get? We're going to get X is equal to 22414 divided by 1 times 10 to the power 6. So X is equal to 0.22414 M cubed. Okay? It's very fair. It's very, very, very fair. Very, very fair. Yeah. Okay, cool. So we have our volume, blah, 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 blah. Let's go. R is equal to PV over what? NT. Giving us R is equal to P has to be in Newton per meter squared. 101,325 Newton per meter squared. Times volume. Volume has to be in meter cubed. 0.022414. Now meter cubed, I'll write it as meter times meter times meter. And I'll write this as over 1, eh? All this is just the numerator, that's just P and V, eh? Divided by, let me write. Divided by 1 more times 273.15 Kelvin. That's fair. Very, very fair. Aye. Because it was only 1. You understand the logic? Right. Anyway, I'm not interested in the value for now. Let's do some gymnastics with the units. The value should be 8.314 roughly. Now, units. Meter squared will cancel out with 2 of these units. You understand? Yes. And the overall unit on top will be Newton times meter. You get what I'm trying to say?
Yes.
Then below to just be more Kelvin. What value have you found with the 9 candles? 8 point what? 3 1 what? 314. Anyway. So R is basically just 8.314, okay? And that's the actual value that you're supposed to know. So I was actually supposed to say there are two values of R. One is rarely used, one is shy. So there's 0.08206 and there's 8.314. The only difference is the units. So this is going to be Newton meter per Kelvin mole, but we are not done. Newton meter, that is, remember, force times distance. Force in the same direction as the distance, right? So Newton meter is as good as a joule. So the correct and complete form of this thing is R is equal to 8.314 joules per Kelvin mole. So I'm going to ask you, what are the two units for the gas constant? What are the two values for the gas constant? And this value of R is rarely used. It's only used for your level in two equations. The whole of your first year, two equations. All the other equations use the other value. You understand? So this is rarely used. Yeah. So, Valwapula, you don't need to do any more tricks. I've gotten the message. Okuya fi okuya. And then I couldn't teach anything else because it was too advanced. Anyway. Problem, you people do not trust me when I tell you this is advanced. You think I'm just oversaying things. Vale? At least math we've moved. Chemistry we've moved. Right? My dot kasera sana. Okay, Vane? Bye-bye.